What's going on, everyone? So this example problem will help you as preparation for the upcoming exam. And this question matches question number 6 on your review. Okay, and it's about non-conservative forces. We didn't talk about them explicitly, which is to say, I did not define what that was, but we still used it. We used it for lab number 3, okay? And so before I explain what they are, let's just get right to the problem. It says, a 60 kilogram skier with an initial speed of 12 meters per second coasts up a 2.5 meter high rise as shown in the figure below. Find your final speed at the top. Given that the coefficient of friction between your skis and the snow is 0.08, acceleration due to gravity is 9.8 meters per second squared, round to the nearest hundredth. And then we have a hint, which is find the work done by friction. You'll also need to find the distance traveled up the incline, assuming a straight line path as shown in the figure. Okay, don't forget that hints are meant for us, or are meant to help make the problem a little bit easier, which is to say that it makes the concept a bit more clear. Okay, so we have to work with friction, right? And then friction is an example of a non-conservative force, and the definition is implied in the name, right? So those are forces that affect the energy. Don't forget that we defined work as both a force across a distance at a specific direction or a change in kinetic energy. So, of course, friction will affect the system by means of dissipation of energy. If you remember lab 3 when we had the cart rolling down the incline, the energy was not fully conserved, right? So we had some dissipation of energy outside of the system because of friction. So friction is a non-conservative force. So that's the first thing we're going to write down. Friction is a non-conservative force. And what these forces do is, so let's change color. Let's go for red. These forces, oh, that was bad. Let's try it again. They add or remove energy from the system. And when we had the pie charts activity with the arrows going out, that is a transfer outside of the system boundary, or arrow coming in, that is energy across the system boundary, so getting energy into the boundary from the system. So that's kind of what we had. So that it has to do with work, right? So how would a force remove or add energy? By means of work done, right? So, and this actually covers the two definitions we had for work. Something related to force and another thing related to energy. Okay, so now how can we find the work done by friction? Okay, so the work done in this case, let's keep purple. So, and then we label friction with lowercase f would be, since we have to use a force, we'll use the force definition of work, which is the force of friction times the distance times the cosine of theta. Okay, before we move on, I want to give you an equation for non-conservative forces, okay, and then I'll explain what that means. So if you have a non-conservative force, use this equation. So if working with non-conservative forces, with non-conservative forces. And then, okay, this is the equation. Work done by non-conservative forces, that's fine. NC is non-conservative. That is equal to the change in kinetic energy plus the change. Don't forget that delta is change in potential energy. Okay? And then we'll expand this one. Work done by non-conservative forces. So change in kinetic energy, that would be kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. Now what I'm going to do is I'm going to move the initial kinetic and potential energies to the left side. So I can have a different version of the equation. So I'll have kinetic energy initial plus potential energy initial. I forgot the I over here. And well, I have to do it in both sides, right? I didn't do it on this side. I skipped a step. Don't do that, guys. Don't skip no steps. Yeah, we can fix this. I'll just move this one over here because I know these two cancel. Now I'll move this one again. There you go. Plus work done by non-conservative forces equals kinetic energy final plus potential energy final. Okay. Now that we have this equation, well, the non-conservative force for this problem is friction. Okay. So I know at some point I'm going to have to use an equation that looks like this. Kinetic energy initial, plus potential energy initial plus work done by friction. That's the non-conservative force. That's equal to kinetic energy final plus potential energy initial. Okay. So now we have an idea of what it is that we need to do after this equation. So I think I should box them. That way you can get them in your notes. There you go. That's one of them. Let's do the second one, the one I'm going to use. And this one's general, right? So another non-conservative force could be something that's to do with sound energy. Okay, but now let's get back to this problem. So to get the work done, we need to find the force of friction and also the distance. Okay, so how do we find the distance? And it says distance traveled up the incline, assuming a straight line path. So now we're going to consider, let's go for blue for this one. No, I think red. So we're going to take this as our initial point, and this is going to be our final point. So this is where the height is 2.5 meters. So that distance let's fix this. There you go. This distance is what we need to find. We'll call the distance d, right? That is the distance across, well, better said, that is the distance on which force of friction is acting, right? Because we have the force of friction here. And then what happens afterwards, after this point, we're not really concerned. We just want to know what happens here, right? Because we want to know how is the energy changing, right? Kinetic energy initial, that's what we have it over here. How is this changing as the skier goes up the incline? So we want to find that distance. And we also know that from here to here is 2.5 centimeters, right? So I'm sure you can see the triangle right there. That is the shape we're always after, the right triangle. There you go. Okay, so before we continue, not that we saw more or less what we need to do, so we need to find the work done by friction, and we found the distance, well, at least we labeled the distance. Let's write down the given, that way we don't miss anything, okay? That way we don't miss anything. So I'll stick with purple. So given. We know that the person is, their mass is 60 kilograms. Let's do that K again. That's fine. And then we have an initial speed of 12 meters per second. We'll call that one initial velocity, V naught. 12 meters per second. And then up a 2.5 meter high rise, so we'll call that one height H, 2.5 meters. And we have the coefficient of friction, or we have to find the final speed, right? So that is very, very important. Let's highlight. And the coefficient of friction is, now the coefficient of friction is the Greek letter mu. It looks like an M, looks like a U, so it's mu, okay? And it is just a coefficient, so it has no units. And then we have acceleration due to gravity, which is 9.8 meters per second squared. And we have to find the final velocity. So just V. Okay. As you can see, our given is not really related, well, it's not yet, to all this stuff, right? I mean, I know kinetic energy, we have velocity, so maybe we could use it. Potential energy, you have the mass, gravity, and height. So, I mean, acceleration due to gravity and height. So, yeah, maybe you could use it, right? But let's focus on the hint. They say find the work done by friction, right? That's the non-conservative force. Okay. And to know the work done, we need both the force of friction and the distance d. So let's find distance d first, okay? Let's find it first. So to do that, I'm going to copy this triangle. Well, it's going to copy some words, so. I'm going to copy it here. There you go. So let's find distance d. I'm sure everyone can see the 90-degree angle, which is here. And then we have this one. Now, some of you will say, yeah, it is 60, I think 35 degrees. Let's label it. Let's give it a letter. This is not theta. You might be asking why. Theta belongs only to the actual motion, right? To whatever is happening with the motion, not the surface. Theta and this 35-degree angle are not the same, okay? So we'll give it a different name. You'll see why. This is important. So we'll call it alpha. This is angle alpha, okay? And we know that this is 2.5, which is the height of this triangle. So H. Now, if we have the angle alpha, and I think we should list it. I didn't write it as part of my given. So alpha is 35 degrees. Again, I didn't write it because I didn't want you to get confused. Because normally we would say, oh, theta is 35. But theta belongs to what's happening here with the motion. So forces affecting the actual motion, not part of the this triangle. Okay. And if we have an angle, the opposite side, and then the hypotenuse, opposite and hypotenuse are part of the sine function, right? So we can say the sine of alpha is equal to opposite divided by hypotenuse. We solve for the height, sorry, for distance, because we need to know what the distance is. Oh, d sine alpha. Let's try the alpha again. Equals height. We divide by the sine of alpha. And now we have the distance. We could find it now because we know height is 2.5 and then that alpha is 35 degrees. But for now, I'm going to leave it like this. Okay? So we found the distance. How do we find the work done by friction? Well, we need the force of friction, right? That's part of the equation. So the force of friction, we have an equation, and that one said friction is equal to the coefficient of static friction times the normal force. Okay, so do you guys see the trend? Force of friction, normal force. Then we have the weight of this person, which is a force. So we have to use some forces. Okay? And to do that, I'm going to copy this triangle again because we have to do a free body diagram. If we have forces, we should do a free body diagram. It's part of the stuff we learned in unit number 2. So I will change some things, right? In this case, we don't want distance d. This is actually just a triangle, so I'm going to replace all this stuff with a triangle that looks similar, something similar to this. There you go, that's one leg. Let's do the other one. Then you will just fix the triangle as needed. This represents the snow, okay? There you go. Now I'm going to make this bigger just for illustration purposes so you guys can see better what's going on. Okay, there you go. That is a triangle. And I'm going to, here's my 90-degree angle. And we know this is alpha as well. This is 35 degrees. We called it alpha. Okay, so now we have to draw the person. I am not going to do that. I'm going to say that the person, since they're wearing blue, has pick green. The person is a rectangular prism. There you go. Kind of like this. That's the person. Next unit we'll have, not next unit, but unit number 5. We can have things such as assume a cow is a perfect sphere, or assume a penguin is a cylinder, and that's kind of fun. Okay, so this is the person, right? This represents the person. We know that because the person is on planet Earth, then they have a weight, that is mass times acceleration due to gravity, and it points straight down. And don't forget, if this person were to fall, right, for some reason, the snow disappeared, they would fall straight down. Okay, and then we'll call that one mg, because that is the weight of the person. Mg. Okay, and then we have, so if they're going upwards, right, they're moving up, then the force of friction opposes the motion. So let's state the motion, direction of motion. That's always a good thing to do. You state the direction of motion. So the skier would go upwards, right? So that is the direction of motion. We'll write the word motion so we know what this means. So if the motion is up, then friction goes down. So the force of friction would be from here There you go. That is the force of friction, like that. And we have one more force, right? Don't forget that the equation for friction had the normal force. Normal force is a reaction force. A reaction force, normally because an object is on a surface. So normal force, the word normal is, what it means is the force which makes a 90-degree angle. That is what normal means in mathematics. A 90-degree angle with the surface. In this case, the surface is the snow or the inclined plane. So that means our normal force should make a 90-degree angle with this. So make sure it goes in the center of mass. There you go. That's somewhat okay. There you go, more or less. Let me see if it has the length I want it to be. Yes, it does. And I moved it again. This is hard. There you go. That's good enough. And we'll label this as normal force. Weird end. That was too weird. There you go. Okay. Now we said this is a reaction force. If you recall Newton's third law of motion, it says for every action force, there's an equal and opposite reaction. If this is a reaction, we need an action force. In this case, a force that is equal in magnitude but opposite in direction to the normal force. What that means is there has to be a force that is acting down like this. And some of you might know already, this is a component of the weight, component of the force of gravity, right? And to know which component, we have to remember that our coordinate system, right, we should have a coordinate system in mind. We tilt it in physics so that it matches the direction of motion, right? So the y-axis is always perpendicular to the x-axis. So there you go. Now let's draw the y-axis. It has to be parallel. There you go. And now we label this as our y, and this is x. Okay. Now it matches the direction of motion. So what that means is this green vector represents the component of gravity that is perpendicular to the surface or along the y direction. Look, the y is like this, and it matches this one. So this is mgy. That is the component of gravity or the weight along the y direction. And then, now, let's say if for some reason the skier stopped at this point, then she would start going down the incline because of gravity. That means we have another vector, which is on this side for friction, right? So it would be mg x plus the force of friction, right? Because both of them are against the motion. So there you go. Now, after we draw the free body diagram, right, that's all we have, that's all we need, we should sum the forces. What does it mean to sum the forces? That means you have to add them up. Very, very simple. Okay? So now let's add them up, and then you'll see how this is going to help us. So let's start with the y direction. The summation of forces along the y equals, so this is the y-axis, right? Look how it matches this one. It would be the normal force minus mgy. Now, what is this equal to? Well, are they jumping up and down the snow here? No, right? They're just sliding upwards. So There's no motion along this direction, so we say 0. And then the only way these two, right, variables, unknowns, when subtracted can be equal to 0 is if they are equal to each other. There you go. Okay, so now we can sum the forces along the x direction. In this case, we don't really have to because we're concerned about force of friction, and friction has the normal force, but let's do it just for practice, for fun, right? So we have the summation of forces along the x. So which one's positive? So the one that matches the motion. In this case, none of the forces are positive. So we have negative mgx minus the force of friction. Now, since they're slowing down, right? This person's slowing down, so there's some acceleration, some negative acceleration. And that'll be, we'll get a negative number after this, right? But again, we don't really need this one. There's an acceleration because they're slowing down, so that'll be a negative acceleration. Okay, so now we sum the forces. What can we do? Well, we said we needed the work done by friction, and to know the work done by friction, we need both the force of friction and the distance at which the force is applied, because non-conservative forces depend on the path, right? So now we can use this definition. Normal equals mgy, and force of friction equals mu times the normal. However, we don't have mgy. There's nowhere in the problem where it says the component of gravity that is perpendicular to the surface or the normal forces, whatever. No. So we have to now use these forces. Okay? And I'm going to take only the components of gravity, because I want to find the component of gravity along the y, because that'll tell me what is the normal force. Okay, so I will fix a few things. I want to make this green because I'm concerned about the components of gravity. I'll get rid of this stuff. I'll get rid of the force of friction. And now we only have the components. Let's make this bigger so you guys can see what's going on. There you go. Now we can move the vectors. So I'm going to move this one down here, and I need to fix it, right? So I'll make this vector a little shorter, this one a little longer. There you go. And I'm going to move mg, and I'm going to move mgx. Let's make it a little bit smaller. I should also move mgy. There you go. Now, I'm sure you guys can see the 90-degree angle, which is here. Now, this triangle is a reflection of this one, right? So, where would alpha be? Well, this one's alpha. That is very important because that way we can use trigonometry to know which function we have to use to define mgy and mgx. So let's start with the sine, right? So the opposite side, well, the sine of alpha, don't forget about SOHCAHTOA, the sine of alpha equals opposite divided by hypotenuse. We solve for mgx, and we have that mgx is equal to mg sine theta. I'm sure some of you already know what mgy is going to be, so let's just work on it for fun. So we know that the cosine of alpha, that's the next function, equals adjacent, which is mgy, divided by mg, that is the hypotenuse. We solve for mgy. Mgy is the component of the force of gravity, that is the weight, which is perpendicular to the surface. So now we have mgy is equal to mg cosine theta. Not theta, I'm sorry, alpha. We'll define theta right now. So there you go. That's the one we want. Okay? So now let's try to find the force, the work done by friction. Okay? Let's find the work done by friction, and then we'll find the velocity afterwards. So the work done by friction will be the force of friction times the normal, times the distance times the cosine of theta. Before we substitute, so what is theta? Theta belongs to this one, to the force applied, right? Now, let's think about the force of friction, right? Because this theta belongs to this force. The cosine theta, this angle belongs to the force, okay? Not to the inclined plane or the surface, whatever, belongs to the force. So to know what theta is, I can move my direction of motion and then get these two together, right? So now what I have to know is from the tip of this vector to this part of the arrow, right, from here to here, how much of a circle can I draw? It's going to be very bad, but I can do half a circle. How many degrees does half a circle? It is 180. Okay? Again, to know what theta is, I have to identify the direction of motion, which is upwards, right? The sphere is moving upwards, up the incline, and then compare it to the direction of the force. In this case, the force I'm looking at for us is the force of friction. They're opposite, right? They have opposite directions. So from, let's say if this were a vector, from tip to tip, it would be half a circle. How many degrees? 180 degrees, okay? Now, if you don't remember that, just think about, is this with or against the motion? In this case, it's against the motion, so theta will be 180 degrees. Now, this is very important. You can ask me, well, why is it important? Okay, if you get the cosine of 180, oh, I don't have the zero. There you go. That is -1. When we talked about force, we said that the work done, when we talked about work, we said that the work done was maximized when the angle was 0, right? Because the cosine of 0 is 1. So this is maximizing the work in the opposite direction, right? So it's -1. So then the work done by friction is force of friction times distance times the cosine of 180 degrees. That is -1. Work done by friction equals force times distance times times -1. That is simply negative force times distance. Now let's do a counterexample, okay? Let's say we had a rope pulling on the person, right? And so that would be force of tension. Let's do a black vector. Force of tension up the incline, right? Now to know what theta is, I would have to place my direction of motion on top of the other vector. And what is the distance from tip to tip? How much of a circle can I draw from this tip to this tip, right when they're on top of each other? Well, I can't even move, right? So the angle would be 0. So if the force is with the motion, then theta is 0, assuming they're parallel, okay? Assuming they're parallel. So whenever you get an angle, don't just assume this is theta, okay? Because theta belongs to the force, this force that is doing the work. Okay. So let's move this one again, that is direction of motion. And let's go back to our problem. Okay, so now we can find the work done by friction. So the force of friction is, where did I write it? Okay. Oh, not yet. Is coefficient of friction times the normal. So work done by friction, oh, I don't want that color. Work done by friction is the coefficient of friction times the normal force times distance d. Okay, I forgot the negative sign. Don't ever forget the negative sign. They can make you or break you. Okay, and now we know that the normal force is mgy. So negative mu times mgy times the distance. And we know that mgy is mg cosine alpha. mg cosine alpha times the distance. And let's get our letters together. Mu, the coefficient of friction, is a Greek letter, so it qualifies as a letter. So negative mu mgd cosine theta. Alpha. There you go. Now we didn't find numerically, we found the equation for the work done by friction. Now we can finally use this one, and I'm just going to copy it. And then we'll replace whatever we need. Oh, not this one. This one. Because that one has the work done by friction. Come on. Okay. Because we have to find the final velocity, right? And we'll see how the final velocity will be expressed here. So we know that the equation for kinetic energy is 1/2 mass times velocity. So it's initial kinetic energy. So it'll be initial velocity squared. Now, do we have potential energy? That's the question. Well, if we're assuming this is the height, right? This is y initial, y final. Delta y, or the height, is 2.5. So over here, they're on ground level, so there's no potential energy. They cannot fall down. Don't think about falling over, just fall down, right? They're on ground level, so there's no potential energy initially. There is work done by friction, and it's a negative work. And it makes sense, right? We said that work would be negative if it was against the motion. She's going this way, she's going this way. So friction is acting against the motion. So it's doing a negative work. Minus coefficient of friction, mg d cosine alpha is equal to, do we have a final kinetic energy? Well, probably, because they want us to find the final velocity. So yeah, probably we have final velocity. There's the possibility that it'll be 0. But let's assume there is some velocity, right? Even if we find a velocity of 0. So 1/2 mv final squared. Is there potential energy? Well, now we do have potential energy because we have a height. And we said that potential energy gravitational was the energy of height. It was mgh. So we have to find final velocity, which is this one. Not squared, but just that one. And hopefully you guys can see we can cancel the mass because it's repeated on every single term. Before this, we cannot cancel anything because we don't know if mass is present in every single term. Okay, but now we saw it, so we canceled it. So we have 1/2 v naught squared minus mu g d cosine alpha equals 1/2 v squared plus gh. Now we don't have the distance either, but we found it here. Now you're going to see why I wanted to keep this one, okay? You can actually find a number if you want, but just for fun, let's keep it in variable form. I can't speak today, or any day actually. Minus mu g, distance was height, divided by the sine of alpha in parentheses, That's distance times the cosine of alpha. That is 1/2 v squared plus gh. Now mathematically, what I can do is I could make these two into a fraction, right? Divided by 1, and I multiply across. So that would be mu h times mu gh times the cosine of theta. That is the numerator. And then 1 times sine of theta times 1 is just the sine of theta. Okay? So I'm going to bring this as part of the numerator, and then this also as part of the numerator. You can be asking, but mister, why? It makes it complicated. It looks like it's going to be more complicated, but it's actually going to make things easier. There you go. Times the divided by the sine of alpha equals 1/2 v squared plus gh. Okay. So the sine and the cosine want to be together. So I'm going to make the fraction just with these two. That is mathematically correct. Again, you don't have to do that to get the numerical answer, but it's good practice. Times cosine alpha divided by sine alpha. That's equal to 1/2 v squared plus gh. So maybe some of you are saying, oh, that's tangent. No, you're wrong. Sine over cosine, well, sine theta or sine alpha over cosine alpha is tangent. This one is the cotangent. Okay? Minus mu gh times the cotangent of alpha equals 1/2 v squared plus gh. Now we can start solving for v final squared. So I'm going to move gh by subtracting gh on both sides. So we have 1/2 v naught squared minus mu gh times the cotangent of alpha minus gh is equal to 1/2 v squared. Notice these two are repeated, right? gh and gh, so I can factor it out. So that'll be 1/2 v naught squared minus gh times mu cotangent alpha. Now, you may be thinking minus 1. But no, because this is minus minus, that'll make it a positive plus 1. Because if I were to distribute this, right, minus gh times this will give me this term, and then minus gh times positive 1, that'll give me minus gh. I'm telling you, a negative sign can make you or break you. So now we can get rid of this 1/2. This is where it gets tricky, right? Because you can see this 2 will cancel this 1/2, and we have to multiply the entire thing times 2. Which means we have to distribute the 2 here and here. And yes, this 2 will cancel these 2. But now, it will not cancel for this term. So we have to keep the 2 over there. So this cancels. So v naught squared minus 2 gh mu cotangent of alpha plus 1 equals v squared. One more step, guys. Let's get rid of the square by taking the square root. I'm not going to do that straight line because it's not going to be straight. So I'll just use OneNote to help me because I can. There you go. And then we have, so let me just copy the equation, right? Because we know we cancel this. So I just copy it. And then I clean it up. Oh man, that's fine. I want the velocity on this side anyways. And there you go. That's how you find the velocity. Now, what if your calculator doesn't have the cotangent? Because I know decimals, they don't have it. So we can write it this way, right? The cotangent, in this case of alpha, is the same as 1 over the tangent of alpha. So that means you can write your equation. So I'm going to do the square root at the end. V naught squared minus 2gh brackets times 1 over the tangent of alpha. I guess I could have used parentheses, right? I don't know why I said brackets. Tangent of alpha. Oh no, I needed brackets because I need mu. I missed mu. Let's start over with this one. 2gh brackets mu times 1 over the tangent of alpha plus 1, close brackets, and at the square root. So however way you do it, it's going to give the correct answer, provided you plug in everything into the calculator correctly. I trust you with that very much. Let's fix this square root so it looks better. And there you go. I'm not going to solve it right now because this is a very long video. But again, guys, my suggestion is pause it, try to grasp what we're saying. And a good way to study, and I told you this, try to explain this to someone. Maybe not the whole thing, all the numbers, but explain what's happening. Why is it that you have a non-conservative force? What is a non-conservative force, right? Okay, so why do we have to find the work done? How do we know friction is doing work? What happens to the energy? And so on. Okay? And that is it. Bye.